In this video, we'll explore properties of sample means. Specifically, let x1, x2, up to xn be an IID sample from some population model. Further, suppose we want to understand and model the behavior of the sample mean of these values. The sample mean, x bar, is calculated by summing up all of the values in the sample and dividing by the sample size n. The study of averages or means is quite common in practice, hence fundamental to exploring data. For example, we might want to study the average height among children, or the average circumference of a tree species, and so on. And just as we observed for other sample statistics, the value of the sample mean x bar can vary from sample to sample, depending upon what data we happen to get. For example, suppose we sample 5 independent outcomes from a uniform 0-1 model. The table below shows 2 possible sample outcomes. In the first sample in the first row, our 5 sample values range from a minimum of 0.00802 to a maximum of 0.879, with a mean of 0.410. The 5 sample values in our second sample range from a minimum of 0.0219 to a maximum of 0.888, with a mean of 0.761. To study the properties of the sample mean, we don't have to start from scratch. Since the sample mean is calculated by dividing the sample sum by the sample size n, we can utilize properties that we've already established for sample sums. In general, suppose we take an IID sample x1, x2, up to xn from a population with the following properties. Each individual xi in the population has an expected value of mu, a variance of sigma squared, and moment generating function mx of t. Then we've shown previously that the sum of the n sample values has the following properties. The expected sum is n times the expected value of the individual outcomes mu. The variance in the sum from sample to sample is n times the variance of the individual outcomes sigma squared. And the MGF of the sum is the MGF of the individual outcomes raised to the nth power. Now let's use these results to establish properties of the sample mean, starting with its expected value. Suppose in general that our IID sample is drawn from a population model with mean mu. To calculate the expected value of the sample mean, we can start by rewriting it as the sample sum divided by the sample size n. Earlier in our course, we proved that we can take any constants outside the expected value. Thus, we have 1 divided by n times the expected value of the sample sum. And as we were just reminded, the expected value of the sample sum is n times mu, the expected value of the individual outcomes. Then these n's cancel out, proving that the expected value of the sample mean is simply mu. Stepping back, notice that the expected value of the sample mean is just equal to the expected value of any individual outcome in the sample. And this makes some intuitive sense. Consider an example. Suppose that the average height of 10-year-olds is 125 centimeters. Further, suppose that we take a sample of 5 10-year-olds. Then by our math, the expected mean height in this sample is just the expected height of any individual 10-year-old. That is, we expect the mean height among our sample of 5 kids to be 125 centimeters, no bigger and no smaller than the expected height of an individual kid. Next, we can study the degree to which the sample mean can vary from sample to sample. Here, suppose that our IID sample is drawn from a population model with variance sigma squared. To calculate the variance of the sample mean, we can start by handling the constant of 1 over n. Earlier in the semester, we proved that we can take constants outside of a variance, but we have to square them. Thus, we have 1 over n squared times the variance of the remaining sample sum. And as we were just reminded, the variance of the sample sum is n times sigma squared, the variance of the individual outcomes. We can then cancel out an n, proving that the variance of the sample mean is sigma squared divided by n. Stepping back, notice that the variance of the sample mean is equal to the variance among the individual outcomes, sigma squared, divided by the sample size, n. Since n has to be at least 2, that is, we have to have at least 2 objects in our sample, sigma squared n is less than sigma squared. That is, in words, there's less variability, hence range, in the sample mean from sample to sample than there is among individual outcomes. Further, sigma squared divided by n decreases as n increases. That is, there's less variability, hence range, in the sample mean from sample to sample as sample size n increases. Essentially, the more data we have, the more stable the sample mean will be. And this makes some intuitive sense. We'll consider an example now, but later simulations in class will also help build our intuition. Here, suppose that the variance in height from 10-year-old to 10-year-old is 5 centimeters. Then if we take different samples of 5 10-year-olds each, the mean height will vary from sample to sample, with a variance of 5 divided by 5, or 1 centimeter. This is less than the variability, hence range in heights among individual kids. Essentially, there's more stability in the sample mean than there is among individuals. Now, suppose we increase our samples from 5 to 25 10-year-olds. In samples of size 25, the sample mean will vary from sample to sample with a variance of 5 divided by 25, or 0.2 centimeters. Thus, there's less variability or more consistency in the sample mean if we calculate it using more data, or in this case, more kids. Finally, suppose that our IID sample is drawn from some population with moment-generating function mx of t. We can then use this to build the MGF of the sample mean. By definition, this MGF is the expected value of e to the t times sample mean x bar. We can then substitute in the definition of the sample mean as the sample sum divided by sample size n. Next, notice that by definition, this expected value of e to the something times a variable, this expected value is the moment generating function of x sum evaluated at that something, or t divided by n in this case. Taking this leap can sometimes take practice, and to convince ourselves, we can do the reverse. Convince ourselves that the moment generating function of x sum evaluated at t divided by n is the expected value of e to the sum times that value t divided by n. And then by the properties of the sample sum, which we refreshed ourselves on earlier, the MGF of the sample sum at any value is the MGF of the individuals in the population at that value raised to the nth power. Thus, the MGF of our sample mean is the MGF of the population MGF, m of x, evaluated at t divided by sample size n, all to the nth power. In conclusion, we've established the following properties for the sample mean x bar calculated from an IID sample.